Welcome to the deep dive. Ever wonder about those invisible gates? What decides who gets to see that secret company file and who just gets locked out?
Right, or why your key card works for the front door maybe, but definitely not the server room.
Exactly. Well, today we're analyzing those unseen guards of modern security. We're doing a deep dive into access control.
That's the plan. And for you listening, our mission here is really to unpack your source material, define what access controls actually are, break down the four key parts that make them work.
And crucially, show how these sophisticated models and systems, things like SSO, Kerberos, the AAA framework, how they're used today to manage security, often at a massive scale.
Yeah, we're definitely moving beyond just talking about passwords. This is about the whole system of trust that, well, pretty much underpins everything digital we do.
Okay, so let's nail down the basics first.
Yeah.
Access controls are essentially the methods used to restrict who gets access to what. And this applies to physical things like, a building or a vault, but also logical resources, a file, a database, even a specific function inside an application.
Right. They're the rules. They
Yeah.
define who is allowed in, what
Yep.
they're allowed to do once they're there, and which specific things they can interact with.
And it's important to distinguish the types, right?
Absolutely crucial.
Mm.
You've got your physical access controls, I think traditional door locks, key cards,
Right.
maybe those biometric scanners at high security doors, basically controlling physical entry.
Okay.
And then you have logical access controls. Now, this is where passwords, encryption keys, network permissions, all that stuff comes in. This governs access to systems, to data.
And the logical ones do more than just yes or no at the door, so to speak.
Oh, much more. They don't just let you in or keep you out. They are constantly monitoring, recording every action you take after you're authorized.
Oh, okay.
And they can dynamically react. For instance, lock your account if you repeatedly try to access something you shouldn't.
Yeah.
They can restrain behavior.
Okay, let's dig into the architecture behind all this, the framework. There are three basic elements in any access control situation, right?
That's right. Three core pieces.
First, there's the object. That's simply the thing being protected. Could be a file, a server, a whole database.
The resource. Yeah.
Text, you have the subject. This is the entity requesting access. And this is important. It might be you, a human user, but often.
Often it's another program, or maybe a background process, a service account needing data, not always a person.
Right. And third, the relationships. These are the permissions. What the subject can actually do to the object, read it, change it, run it, delete it.
Exactly. Read, write, execute, delete, those kinds of actions.
Got it.
And the thing that ties all this together, the real heart of the enforcement, is something called the security kernel.
Okay, the security kernel.
Yeah.
Sounds important.
It is. Think of it like the ultimate gatekeeper, maybe the Supreme Court for your operating system. It's this central core part of the system that intercepts every single request for access. Every time a subject tries to touch an object.
Every single time.
Every single time. It checks the rules, usually in something called an access control list or database, and makes that final allow or deny decision.
Wow.
And the real power here, because it sees everything, it creates this incredibly detailed, you can say tamper-proof record of all activity. That's your audit log.
Ah, the log file for tracking.
Precisely. If something goes wrong, if there's a breach or misuse, that audit log tells you exactly who did what, where they did it, and when. Accountability.
Okay, so this whole process, you mentioned it breaks down into phases.
Yeah,
Got
certainly into two main phases.
Yeah.
The first one is the policy definition phase. This is more organizational, more human-driven.
Setting the rules.
Exactly. This is authorization. It's asking the big questions. Based on someone's job role or their team or maybe their seniority level, who should have access? And access to what specific resources? It's defining the intent.
Makes sense. Policy first.
Then, once you've defined that policy, you move into the policy enforcement phase. This is purely technical. This is where the systems take over.
And this involves the other three parts.
Right. This is where the remaining three pieces of access control happen, usually in sequence. Identification, which is claiming who you are. Authentication, proving that claim is true. And finally, accountability, which we touched on, tracking and logging what happens.
Okay, let's take those one by one. Identification. That's just stating your identity, right? Like saying, hi, I'm user Jado123.
Exactly. It's your claim. Usually your username, or maybe you swipe a smart card, or perhaps it's an initial biometric scan.
And our sources stress a couple of guidelines here for IDs.
Yeah, two key things. First, uniqueness, obvious maybe, but
Yep.
critical. No two users can ever share the same ID. Creates chaos. Second, non-descriptive. Your ID shouldn't give away your role or importance. Avoid things like admin or CEO accounts
Why is that?
because it just makes an attacker's job easier. It hands them a high-value target without them even having to guess. Make IDs opaque, meaningless strings if possible.
Good point. Okay, so identification is the claim. Then comes authentication.
Authentication is the proof.
Okay.
It's the system saying, okay, you claim you're JADO133, prove it. This is where we verify the identity.
And there are different ways to prove it.
Oh yeah, lots of ways.
Yeah.
But we generally group them into a few main categories based on what you use for proof. You often hear about 3 core factors.
Okay.
First, knowledge. Something only you know. The classic example is your password or a PA.
The most common way.
By far the most common. But also, let's be honest, usually the weakest link. Knowledge can be forgotten, guessed, phished, stolen.
What's the second factor?
Second is ownership, something you physically have, like a real key or a smart card you insert, or maybe one of those little cryptographic token fobs that generates a number.
Right, I have one of those.
And third, characteristics, something you are. This is biometrics, your fingerprint, your iris pattern, maybe even your DNA, though that's less common for everyday access.
Okay, knowledge, ownership, characteristics. Since knowledge, passwords are so common but weak, let's talk about strengthening them. What makes a strong password?
Good question. For anyone listening, the basics for a strong password aren't just about length. Though that matters, think at least 8 characters, often more these days. It's really about complexity. You need to mix uppercase letters, lowercase letters, numbers, and critically, at least one special character, like an exclamation point or a hash symbol, and ideally put that special character somewhere early in the password, not just tacked on the end.
Why early?
Some older cracking algorithms were less efficient if the complexity started earlier. Plus, it avoids simple patterns and the absolute don'ts.
Oh, yes, your username.
Definitely not. No personal info, birthdates, social security numbers, pet names, no dictionary words, and please, no simple keyboard walks like QWERTY or 1, 2, 3, 4, 5, 6.
Yeah, those get cracked instantly.
Instantly by automated tools. Strong passwords are your first defense against those brute force attacks.
Okay, so we can make passwords stronger, but what about that second factor, ownership? Tokens.
That's right. Tokens are a great way to add a layer. Ownership authentication. You see this a lot in multi-factor authentication. Most modern tokens follow industry standards like HOTP or TOTP.
HOTP and TOTP.
Yeah, HOTP is the hash-based one-time password. It uses a counter that increments with each use. TOTP is the time-based one-time password. That's the one that usually shows a new code every 30 or 60 seconds.
Ah, okay. I think mine's TOTP then. Are there downsides?
There are trade-offs, always. With TOTP, the time-based one, both your token and the server need to have their clocks very closely synchronized. If they drift apart, your valid code won't work.
Right, frustrating.
Very. With HOPP, the counter-based one, the main risk is getting out of sync. If you, say, generate a code, but then your login fails or you cancel it, the server might not have incremented its counter, but your token has. Now they disagree on the next expected code.
Ah, okay. So synchronization is key for both, just in different ways.
Exactly. It's always this balance between usability, security, and keeping everything lined up correctly.
And the third factor, characteristics biometrics. Fingerprints, retina scans.
Yeah, biometrics. We can sort of split these into 2 types. Static biometrics are things that generally don't change much, like your fingerprint pattern or the unique map of your retina or iris.
Okay.
Then there are dynamic biometrics. These measure an action or a behavior, things like the specific way you sign your name, the rhythm and speed of your typing, even the cadence of your voice, things that involve movement or process.
Interesting. What are the catches with biometrics? They sound pretty foolproof.
Well, they're powerful, but not perfect. The biggest challenge isn't usually the technology itself, it's managing the accuracy. Every biometric system fights a battle between 2 error rates.
Which are?
The false rejection rate, or FRR, and the false acceptance rate, FAR.
False rejection, so rejecting a valid user.
Exactly. The system is maybe too sensitive, or the scan wasn't perfect, and it rejects you, even though you're authorized. That's the FRR. Super annoying for users.
Yeah, definitely. And false acceptance.
That's the opposite, and much more dangerous. The system is too lenient, and it lets an unauthorized person in because it mistakenly thinks they match a valid user. That's the FAR.
So you have to tune the system.
Precisely. You have to find a balance point, the so-called crossover error rate. If you make it super strict to minimize FAR letting bad guys in, you'll inevitably increase FRR annoying your good guys.
Ah, the trade-off again.
Always. And another thing is often speed. Compared to typing a password, biometric scans can sometimes feel a bit slower, that reaction time. It all plays into the user experience versus security equation.
Okay, so we've covered ID and authentication, claiming and proving identity. Now let's circle back to authorization. This is about the rules, right? What you're allowed to do.
Exactly. Authorization is policy-driven. Before the system even checks who you are, it needs a set of rules defining what anyone is allowed to do. And these rules are built on some core security principles.
What are those?
Well, first and foremost is usually implicit deny. This means, unless there's a specific rule that explicitly grants you access, you are denied by default.
Default is no?
Default is no. It's the safest starting point. Then you have the principles of need to know and least privilege. They're related.
Need to know sounds obvious.
It basically means you should only have access to the information or resources that are absolutely essential for you to do your specific job function. Nothing more.
And least privilege.
Very similar, but maybe focus more on permissions or rights. You get the minimum set of privileges required.
Yeah.
If your job is just to read reports, you don't get write or delete permissions. Minimizes potential damage if your account is compromised.
Makes sense.
And a third big one, especially in finance or sensitive operations, is separation of duties.
Splitting tasks up.
Exactly. The idea is to prevent fraud or major errors by ensuring that no single person has control over all parts of a critical process. For example, the person who can create a new vendor in the payment system should not also be the person who can approve payments to that vendor.
Ah. Requires collusion to commit fraud?
Precisely. You distribute trust and make abuse much harder.
Okay, so those are the principles. How do organizations actually put these into practice? What are the models?
Right. There are several formal models used to implement these principles. The simplest, maybe, is discretionary access control, or DAC.
Discretionary, meaning the owner decides.
You got it. Access is granted based on the discretion of the resource owner. Think about files on your own computer or a shared drive. If you create a document, you typically decide who else can read it or edit it.
Like setting permissions in Windows or Linux?
Exactly that. It's very flexible, very common. But the big weakness. Security depends entirely on the owner making smart choices. They can accidentally or even intentionally give access to the wrong people.
Okay, so what's the alternative for more sensitive stuff?
For highly sensitive data, especially in government or military contexts, you use mandatory access control, or MEC.
Mandatory, so non-discretionary.
Completely non-discretionary. The owner of the resource has absolutely no say in who can access it. Access is determined strictly by comparing security labels.
Labels.
Yeah. The resource, the object, has a classification label. Think top secret, secret, confidential. The user, the subject, has a clearance level. Access is granted only if the subject's clearance is equal to or higher than the object's classification.
So it's rigidly enforced by the system based on these labels.
Absolutely. It's highly secure because it removes human error or malicious intent from the access decision regarding classified data. You simply cannot override the system's rules.
Got it. What else is common, maybe more in the business world?
Probably the most popular model in businesses today is role-based access control, RBAC.
Based on your job role.
Exactly. Instead of assigning permissions to individual users, you assign permissions to define roles like accountant, sales manager, HR assistant. Then you assign users to those roles.
And the advantages?
Huge administrative simplification. Think about employee turnover. If the marketing director leaves, you don't have to manually revoke all their individual permissions and grant them to the new person. You just assign the marketing director role to the new hire, and they instantly inherit all the necessary access.
Ah, much easier to manage, especially with lots of users.
Massively easier. You manage maybe dozens of roles instead of potentially thousands of individual user accounts and their permissions.
Okay, DAC, MMAC, RBAC. Is there anything even more fine-grained?
There is. The most granular and arguably the most complex is attribute-based access control, or ABA.
Attributes, like characteristics.
Kind of. ABA makes access decisions based on evaluating attributes, characteristics of multiple components involved in the request.
Such as?
Well, attributes of the subject, maybe their seniority, their department, their training certifications, even their current location.
Yeah.
Attributes of the object, like the file type, its sensitivity level, the project it belongs to. Attributes of the desired action, read, write, approve, delete. And even attributes of the context or environment, like the time of day, the current threat level, the network they're connecting from.
Wow, that sounds complicated. Why use ABAC?
Because modern environments, especially cloud environments, are incredibly dynamic and complex. Think about it. In a traditional office, maybe RBAC based on job title was enough.
Right.
But in the cloud, you might need a rule that says, Allow access only if the user is a senior engineer and they're connecting from a corporate device, and the data sensitivity is internal use only, and it's during business hours, and the system threat level is low.
Okay, I see. You need that level of detail.
You need that fine-grained control to manage risk effectively in these fluid, often non-hierarchical, massive-scale environments. ABAC provides the necessary complexity or maybe flexibility to handle those scenarios.
Managing all these different access controls across potentially hundreds of applications.
Yeah.
That sounds like a nightmare for users, having to log in everywhere.
Oh, it absolutely is. Which leads us directly to the idea of single sign-on, or SSO.
The dream of logging in just once.
Exactly. SSO offers huge convenience. You authenticate strongly one time, maybe using multi-factor authentication, and then you gain access to multiple different authorized systems or applications without having to log in again and again.
But there's a catch, right?
There's always a catch in security. The major drawback of SSO is that it creates a single high-value point of failure. If an attacker manages to compromise that one set of login credentials,
They get the keys to the entire kingdom.
pretty much, they potentially gain access to all the systems and data that the legitimate user could access via SSO. So the initial authentication for SSO needs to be incredibly robust.
Is there a classic example of a secure SSO system?
Absolutely. The quintessential example, developed back at MIT, is Kerberos.
Kerberos, I've heard of that. How does it work?
Well, it uses symmetric key cryptography quite cleverly to establish trust without repeatedly sending your password across the network, which is a huge win. Think of it like getting into an exclusive multi-room club.
Okay, analogy time.
So first, you go to the main entrance, the authentication server, AS. You prove who you are once, maybe with your password. The AS doesn't let you in directly, but it gives you a special encrypted wristband. That's your ticket granting ticket, TGT.
Caught my wristband. Now what?
Now, with that wristband, you can go to another desk inside the ticket granting server, TGS. You show your wristband, TGT, and tell the TGS which specific room or service you want to access, say, the database server room. The TGS verifies your wristband and gives you a different temporary ticket specifically for that room. That's your service ticket.
So a ticket for the specific service.
Right. Then you take that service ticket and show it at the door of the actual target server, the database room. The server checks the ticket, sees it's valid and issued by the trusted TGS, and lets you in.
And the key is?
The key is your actual password was only used right at the very beginning talking to the AS. It never traveled across the network to the TGS or the final target server.
Yeah.
After that first step, all authentication happens using these encrypted tickets. That's the massive security advantage of Kerberos.
Clever. Okay, so SSO helps the user. What about managing all this centrally for the organization?
That's where AAA servers come in. AAA stands for Authentication, Authorization, and Accounting.
Ah, the three components we discussed, plus accounting.
Exactly. Centralizing these functions onto dedicated AAA servers is incredibly common in large enterprises. It's almost essential, really.
Why centralize?
Several big benefits. Administration time is slashed. You manage policies and users in one place. It ensures consistency. Every system uses the same rules for authentication and authorization. And it makes auditing and compliance reporting way easier because all the logs, that's the accounting part, are gathered centrally.
Makes sense. Are there standard ways to do AAA protocols?
Yes, there are two main protocols you'll encounter. The older one is Radius, Remote Authentication Dialing User Service.
Okay, Radius. What are its characteristics?
Radius typically uses UDP for transport. UDP is connectionless, which can be faster but less reliable as it doesn't guarantee packet delivery. And crucially, Radius generally only encrypts the user's password during the authentication exchange. The username, and importantly, all the accounting information about what the user did, are often sent in clear text across the network.
Oh, that doesn't sound ideal.
Not really for high-security environments.
Yeah.
Also, Radius tends to combine the authentication and authorization steps into a single exchange.
Okay, so what's the other main protocol?
The other major one, considered more modern and secure, is TACACS Plus, Terminal Access Control System Plus. It's a Cisco proprietary protocol, but widely used.
TACACS++, how is it different?
Key differences. First, TACACS Plus uses TCP for transport. TCP is connection-oriented, so it's more reliable. It ensures packets arrive in the right order.
Okay, reliability. What about security?
Big difference here. TACACS Plus encrypts the entire payload of the packet between the client device, like a router or switch, and the AAA server. Not just the password, everything. Username, authorization requests, accounting data. It's all encrypted.
Much better.
Definitely more secure for transmitting sensitive information. And another key thing, TACAS Plus explicitly separates the authentication, authorization, and accounting functions into distinct steps or message types.
Why is that separation useful?
It gives administrators much more flexibility and granular control. You can, for instance, use one server for authentication and a completely different system or set of policies for authorization and another for logging. It allows for more complex and tailored security postures.
Got it. So generally, TACAS Plus is seen as more robust and flexible than Radius.
In most modern enterprise network scenarios, yes.
Now, we've talked a lot about centralization. Is there ever a case for decentralized access control?
There can be. While centralization offers huge administrative benefits in very large, highly distributed organizations or maybe in specific cloud setups, some access decisions might still be handled locally, perhaps by department managers or within individual application environments.
What's the risk there?
The main risk is loss of standardization. Different departments might apply policies inconsistently, or permissions could overlap in confusing ways. It makes central auditing harder. However, it does avoid having that single central point of failure.
Right, trade-offs again.
Always. And even in decentralized scenarios, you still need strong authentication. This is where standards from groups like OAuth, the Initiative for Open Authentication, become important. They define protocols like HOTP and TOTP, those token standards we talked about. They help ensure that even if authorization is distributed, the authentication method can still be strong and standardized, using things like mobile authenticator apps. #tag outro.
Wow, okay. This has been a really thorough journey through the infrastructure of digital trust.
It's a complex area.
Definitely. We defined access control. We broke down those 4 parts: identification, authentication, authorization, and accountability. We looked at the different ways we prove who we are, knowing something, having something, being something.
And explored how organizations structure all those permissions using different models, from the owner decides DC to the strict MIC, the very common RBAC.
And that super granular ABC for complex environments, plus the big systems that make it scale, like Kerberos for SSO and the AAA frameworks like Radius and TACAS plus S.
And let's just quickly reinforce that 4th part, accountability. It's easy to focus on getting in, but knowing what happened afterwards is critical.
The logging.
Exactly. Every access, every action allowed or denied should be logged. That detailed trace back to an individual user or process is absolutely fundamental for security audits, for forensic investigations if something bad happens, and for meeting all sorts of compliance rules. It ensures responsibility.
So stepping back, what's the big picture here for you listening as you navigate your digital life?
Well, I think it boils down to this. The complexity we've discussed, all these models and protocols, it's fundamentally about managing trust in a systematic way.
Right. Every login, every keycard swipe, every fingerprint scan.
It's all part of a carefully negotiated agreement between you and the organization or the system. An agreement about who you are, what you're allowed to do, and the fact that your actions are being noted. It's an enforced relationship of trust.
A relationship built on rules and verification. Okay, time for our final provocative thought, then.
Let's do it.
We talked a lot about human users, subjects authenticating, but you also mentioned systems can authenticate based on things like IP addresses or machine identities.
Right, non-user authentication, it happens all the time, especially in data centers and the cloud. Servers talking to other servers, APIs accessing data.
So here's the thought. As these complex cloud environments grow, with more and more automation, more machine-to-machine communication happening without any direct human login, will the whole concept of the subject in access control eventually shift almost entirely away from the human user? Will the primary focus become authenticating and authorizing automated processes and machine identities?
Making human password-style authentication, maybe, almost irrelevant for core network and system-to-system security decisions.
Exactly. Could the models we rely on for human access become secondary to managing the trust relationships between countless automated entities?
That's a fascinating question. It definitely makes you think about where identity and access management is heading in an increasingly automated world, something to mull over next time you hit that login button.